Hello students, Mr. Holderman here with a short introduction to power. We often hear the word power used in everyday language as maybe strength, like that guy is very powerful, or even the amount of electricity that your house uses, um, or even energy itself. But in physics, power has a very specific definition, and that is the rate at which work is done. So it definitely relates to energy because we know that work is the addition of or subtraction of energy from a system, but with the rate, we know that it also relates to the amount of time taken. So it's the amount of time at, over which work is done. So it gives us the work-time ratio, which actually is kind of the equation itself. We get that power is equal to the work divided by the amount of time taken. But let's go a little bit deeper with that because we know that work is equal to force times displacement. So if we look at that, force times displacement over time, that's also the amount of power, the power output. But one thing that we can do is classify this and just kind of do air parentheses here. If we have a force times the quantity displacement over time, well, what is displacement over time? That's a velocity. So we can also think of this as a force times a velocity. Get a little bit more specific with that, this would be the force required to move an object at a constant velocity. So if you know those variables, then you can also calculate the amount of power output. So we know that now that the definition is of power is work per time, so we can look at the units there, and work is it's a measure of energy, so it's in joules, and time is seconds, as it has been all year. So our measure of power would be in joules per second, but we can do better than that and give credit to the guy who gave his name to this unit and call it a watt. So the SI unit for power is a watt, capital W. Now historically, the unit for power was a horsepower, which represents about 750 watts. And this came about during the Industrial Revolution when we had machines replacing horses that historically had done the work. So um, you have a machine, if it can do 1 horsepower worth of power, then it can do the work of 1 horse. I guess the standard horse can do 750 watts worth of power. All machines, including people, have power ratings, which is the rate at which the machine can do work on other objects. So one fun activity that you can do is strap some weights onto your back or put on a heavy backpack with all of your physics textbooks and run up a flight of stairs. If you know how much you weigh with the books on your bag, on your back, you can calculate your weight or the force. And then if you know the distance up the stairs, the elevation, you can calculate your gravitational potential energy. And if you measure the amount of, or calculate the amount of time taken to run up the flight of stairs, you can calculate the change in gravitational potential energy. And then with that, you can find your power output. So the amount of the change in your gravitational potential energy divided by the time it took you to run up the stairs, and there you go. You can relate yourself to see how good you are compared to a horse. Now the equation itself is pretty easy, but it's important to look at the relationships between the variables involved. So we know that power is proportional to the amount of work done and is inversely proportional to the time taken. So we have our two lifters here, this weakling on the left and the strong guy on the right. So if we're just looking at the amount of work done, given the same amount of time, we could say that the strong guy on the right, if he can lift twice as much weight as the guy on the left in the same amount of time, then his power output would be twice as great. And then if we're looking at the time variable, like in this picture, we see the weak guy on the left and the strong guy on the right lifting the same amount of weight, but if the strong guy can do it in 1 second, but the weak guy does it in 5 seconds, then the power output of the strong guy would be 5 times that of the guy on the left. Now we can easily plug in numbers to the equation. I think the variables are easy enough to work with, but hopefully this gave you a conceptual overview of what power is and how we can calculate it.